Hello, everyone. I'm Richard, a second-year PhD student at Stanford. I'm going to talk about parallel sampling while counting, which is based on my joint work with Nima and Aviad, who are both professors at Stanford. The focus of this talk is on sampling from huge distributions. Consider I'm talking to a bot and asking it to generate a random picture of a dog for me. The dog may then the bot may then think about a function mapping a word and a picture to a Boolean value indicating whether the word characterizes the picture. For example, the word dog I asked characterizes the left three pictures and the value of the function is 1. On the other hand, it does not characterize the right three pictures and the value of the function is 0. Because I'm asking for a random dog, the bot will uniformly sample the picture that have value 1 with the word dog and reply me by that picture. Because the number of possible pictures is exponential in the number of pixels, which can be easily more than 1 million in more than pictures, the robot needs some sampling algorithm that could efficiently sample from this kind of exponential size distributions. Formally, in the sampling problem, we are given a function f defined on hypergrids, where the dimension of the hypergrid corresponds to the number of pixels, while this q corresponds to the number of possible colors in our previous example. In F's induced distribution mu, each point on the hypergrid has a probability proportional to fx. The approximate sampling task asks us to output a random point whose distribution is within a total variation distance of arbitrarily small delta from mu in a polynomial time. A fundamental theorem of Jerome Valiant and Vazirani in 1986 shows that approximate sampling is simply equivalent to approximate counting for this kind of self-reducible problems. Well, the counting problem asks us to give the sum of all possible fx. So one way to solve the sampling problem is to access the counting oracle of f. More specifically, for self-reducible problems, the counting oracle takes any subset of coordinates s and any vector s restricted to s as input, and output the sum of fx for all x that agree with y on these coordinates. Because this s can be arbitrary, this counting oracle is also equivalent to the conditional marginal oracle, which gives the marginal distribution of any xi under any possible conditioning. With this marginal oracle, we have a very simple sampling algorithm that works as follows. First, it asks for the marginal distribution of x1 and generates a sample sigma 1 for x1. Then it asks for the marginal distribution of x2 conditioning on x1 equaling sigma 1 and generates sigma 2 for x2. By repeating this process for n times, we can get a sample sigma 1 to sigma n. The number of correlates of this algorithm is n, which can be shown to be optimal. However, this algorithm is inherently sequential. It needs n rounds of correlates in total. In this talk, we will focus on minimizing the number of rounds of the correlates by allowing any polynomial number of correlates in total. The study of parallel sampling while counting could be interesting in theory because there are many parallel efficient counting techniques. The most famous one is determinant or Fabian-based counting that works for a large family of problems like counting spanning trees. This technique is parallel efficient since any linear algebra can be computed in NC time, and other counting techniques include correlation decay and Babinok's method. Besides in theory, the problem of parallel sampling while counting can be weighted in practice, approximate conditional or marginal oracles are very similar with any other autoregressive models, a concept in AI research that is closely related to many popular modern neural networks. Moreover, some theoretical parallel sampling techniques have shown success in speeding up the sampling of diffusion models in practice. So up to now, the problem of parallel sampling is well motivated. The most interesting theoretical question here to ask is then, can we sample with a strictly sublinear run complexity while counting oracles for arbitrary distributions? We answer this positively by giving an exact sampling algorithm with average complexity n to the 2/3 times some polylogarithmic factor of n and q while exact counting oracles. In particular, our algorithm uses only ON queries to the conditional marginal oracle and also works with approximate counting oracles. As an amplification, we show O tilde n to the 1/3 parallel time algorithm for sampling perfect matchings in planar graphs, improving the previous square root of n upper bound. A more ambitious question to ask is then, can we sample with a polylogarithmic in n round complexity while counting oracles? Unfortunately, the answer is no. We complement our positive result with the n to the 1/3 lower bound for algorithms that can only make a polynomial number of queries. This eliminates the possibility that our algorithm can be improved significantly. Prior to our work, there are many results on parallel sampling, including RNC algorithm for sampling under log concavity and the sampling spanning trees, DPPs, and Eulerian tools. There are also quadratic speedups for sampling under the assumption of entropic independence. Besides these structural distributions, there are also works on parallelizing Markov chains, which lead to RNC algorithm for many famous problems that satisfy a Dobrushin-like condition. Next, we will dive into our techniques. Our main focus is on the upper bound side. Recall that our goal is to sample mu, a distribution on an n-dimensional hypergrid. For simplicity, in the rest of the talk, we will assume that we are sampling on a hypercube. In our algorithm, we first permute all the coordinates and fix the randomness for our algorithm. That is, for every variable xi, we have a unique random variable ui in 0 to 1. Using this fixed randomness, the goal of the remaining algorithm could be computing the fixed point of this dynamics. Well, sigma star I equals applying some sampling algorithm using the randomness ui on the conditional marginal distribution of xi, conditioning on x1 to xi minus 1, equaling sigma star 1 to sigma star I minus 1. For q equals 2, the sampler here could be fairly simple by checking whether the randomness is greater than the probability that the Bernoulli variable is 0. Then, on each round, the straightforward attempt is to generate new samples for xi by the existing sample of x1 to I minus 1. After generating these new samples, we will verify if our solution satisfies this dynamic. Suppose at round t, the first case sigma t all agree with the true sigma star, or say they all satisfy the dynamic we want. Then in round t plus 1, the k plus 1 sigma t will definitely agree with sigma star k plus 1. And ideally, we want to have a longer prefix that agree with sigma star. However, due to incorrectness of our previous sample, this couldn't be true. Technically, this could be a more serious problem because it can lead to a linear round complexity for this algorithm. Our second attempt and our algorithm did some modifications on generating new samples on each round. Instead of conditioning on all previous variables for each xi, we only condition on all variables in the longest correct prefix. Technically, the longest correct prefix can be found using the previous sample and the intermediate vector zt we use to verify the correctness of our previous sample. So this step does not increase the round complexity of our algorithm at all. The intuition of why this algorithm can be sublinear is based on this pinning lemma. Informally, the pinning lemma states that random conditioning could lead to low correlations between the unconditioned variables. The correlation could be as low as 1 over square root of n. Therefore, we can expect the algorithm to make a polynomial number of more entries to be correct in each round with a constant probability. Thus, we can expect a strictly sublinear average round complexity then. A fun fact about our algorithm is that a similar looking algorithm, speculative decoding, has been considered by practical AI researchers to parallelize the sampling of neural networks. On the step, we generate new samples. They consider using some smaller neural networks for predictions. While on the step, we verify the correctness. They turn back to the large neural networks that are trained for the tasks. To analyze the round complexity, we define the notion of small progress rounds for the rounds where we only increase m by at most theta, where theta is a parameter to be determined. Let pi given j denote the probability that xi equals 0, conditioning on x1 to xj. Here, pi given j can be viewed as a random variable with respect to x1 to xj. So this pi given j forms a martingale under fixed I and with respect to j. Because of this martingale property, this Pij could vacillate only mildly between I minus theta to I minus 1. Suppose here we fix the randomness for the first I minus 1 variables in a round where we generate new samples conditioning on the first m variables. The probability that the I sample sigma t is incorrect is bounded by the difference between pi given I minus 1 and the pi given n. Then we can prove that the probability that each I gives the first incorrect sample in a small progress round can be bounded by the largest difference between pi and given I minus 1 and the pi given j here. Since the first incorrect samples are different between different rounds, the expected number of small progress rounds can then be upper bounded simply by the expected sum of these maximum differences. Thanks to Dobbs martingale inequality, we can further bound this expected number of small progress rounds by the sum of pi given I minus 1 and the pi given I minus theta. To further bound this quantity, we will use the pinning lemma we mentioned previously. Pinning lemmas are introduced independently by Montanari in 2008 and Raghavendra Tan in 2012. It was used for rounding LPs and STPs in the Shirley-Adams or sum-of-square hierarchies. For our specific sampling task, we propose a new variant. Let mu I given J to be the conditional marginal distribution of xi conditioning on x1 to xj. This is a randomly constructed distribution based on x1 to xj. Our new variant of pinning lemma gives a theta log Q upper bound for the sum of square total variation distances between mu I given I minus 1 and mu I given I minus theta. Since this total variation distance is simply the difference of marginals we want for Q equaling 2, we can easily prove n to the 2/3 upper bound for the number of small progress rounds if we take this theta to be n to the 1/3. Recall that the small progress rounds are defined as the rounds where m increase by less than delta. The number of other rounds, or say large progress rounds, is clearly no greater than n over theta. So if we take theta to be n to the 1/3 here, the total round complexity of our algorithm is then upper bounded by n to the 2/3. One last ingredient for our algorithm is a general sampler for Q greater than 2. This sampler is based on a technique called universal coupling introduced by Liu and Ying for parallelizing the simulation of Markov chains. Universal coupling can be viewed as a decentralized coupling scheme based on public coins. The main idea is to construct a function f mapping from any distribution mu and the public coins R to an outcome. Then with this distribution, our coupling is to output f mu I R for each distribution mu I. Liu and Ying showed that there exists one such function that gives a true approximation for the optimal coupling. In our work, we generalize their results in a multi-distribution setting in which the distribution satisfies some martingale property. This martingale property fits our analysis for Q greater than well because the crucial part in our analysis, the different conditional marginals of xi considered as the random variables with respect to x1 to xi minus 1 forms a martingale. Moreover, for this universal coupling scheme, we give a more practical implementation for it. Before reaching the conclusion, I would like to talk about the high-level ideas about the lower bound. And this construction is fairly common in the literature of adaptivity, and it is already used for many matrix problems and submodular minimization. In the construction, we first randomly partition the coordinates into roughly n to the 1/3 blocks, each with roughly n to the 2/3 coordinates. In each block, we choose a random affine space under F2. The ith affine space have roughly I times n to the 1/3 dimensions. And the local distribution inside each block I is uniformly over its affine space. And the entire distribution is simply the product of these local distributions. In this construction, the partition of the coordinates and the affine spaces are unknown to the algorithm. So a key property of these instances is that for any query, or say any subhypercube of the entire space that have non-zero probability mass in the ith block, then it should have a fixed probability mass in all subsequent blocks with a high probability. This implies that before we know something about block I, we can know almost nothing about all the subsequent blocks. All algorithms can then learn the blocks one by one and have around complexity R. In this talk, the main takeaway is the parallel reduction of sampling to counting with polynomial speedups. And a polynomial speedup is the best we can have in general. Our work also leaves the following open problems. First, whether we can sample planar perfect matchings in a polylogarithmic number of rounds of computation is still open. Second, it could be interesting to close the gap between n to the 2/3 and n to the 1/3 for parallel sampling while counting. The analysis of our new algorithm is shown to be tight, so we need to find some new algorithms to improve this upper bound. Finally, as problems like sampling spanning trees naturally allow us to do weighted counting on it, it could also be interesting to improve the n to the 2/3 upper bound using weighted counting oracles. That's all. Thank you for your listening.